In section 5-3, we're going to look at one application of exponential and logarithmic functions, which is calculating future value of a lump sum investment. So we're going to have two cases here, and I'm going to jump back to this slide in a minute after we look at an example. But the one case would be if we invest a certain amount and it is accruing interest and we are paid at some finite point. So maybe it's once a year, the bank gives me the interest I have earned, or maybe twice a year, or once a month. This would be the discrete case. The other case we're going to consider is a continuous case, where anytime I earn any interest, it is immediately given to me, and then therefore can earn me more interest. So before I give you formulas here, I want us to see if we can motivate these by looking at an example, and then we're going to jump back to this slide and see if we can generalize this to some formula. Alright, so on the next page, all of these cases we are investing $5,000 at 3% interest for 3 years. And we want to see how much money we earn here. Alright, so the first case here, I am paid annually, once a year. So at time 0, I deposit $5,000. I walk away and come back 3 years later to see how much I have if I am paid annually. Okay, so the first year, let's see how much interest we earn. We need 3% of 5,000. So 3% as a decimal, 0.03 times 5,000. Alright, so that first year I earn $150. Okay, so if I add that back to the 5,000 I had, that would be $5,150. Alright, now I'm going to add that back to the 5,000 I had. Okay, now the next year I get 3% here. So I'm going to multiply this by 3%, and we get $154.50. Now let's pause here for a minute. Why would I earn more interest the second year than I did the first year? It's about $4.50 more. Well, the reason for that is this $150 that was added to my account then starts to earn me interest. So the second year I earn a little more. So now I'm going to take that amount, add it back to the $5,150 that I had, and now we're at $5,304.50. Alright, and then lastly, year 3, I'm going to earn 3%, and we get $159.14. And then we're going to add that back to the $5,304.50 I already have, for a total of $5,463.64. All right. Now, so at the end of 3 years, if I'm paid once a year, we have $5,463.64. Now, we're going to look at the second case where I am paid semi-annually. Okay, so what we're looking at here, instead of being paid my 3% once a year, I'm going to get half of that interest midway through the year and the other half at the end. So instead of getting 3 once a year, I'm going to get 1.5% twice a year. Okay, so again, I start with $5,000, but halfway through that year, I'm going to get 1.5% of that. All right, so let's start with 5,000 as we did before, times 1.5%, and I get $75. Okay, so now I have $5,075. Okay, then let's and then at the end of the year, I get the other 1.5%. So I'm going to multiply this by 1.5%, and I get 76.13. Okay, and then I add that back to the $5,075 I already have, and I get $5,151.13. All right, so let's pause here. So when I was paid once a year, at the end of the year, I ended up with $5,150. When I'm paid twice a year, do you see I end up with a little more, $1.13 more? Now the reason for that is if the bank pays me mid-year, this $75 can start earning me interest the second half of the year. So this $75 made me an extra $1.13 in the second half of the year that I did not get when I was only paid once a year. All right, so let's see if we can continue this. Maybe we can speed this up a bit. All right, so I now get a 1.5% here, and then I am going to add that back to the $5,151.13 I already had. Alright, so halfway through the first year, I now have $5,228.40, and then at the end of the second year, I end up with $5,306.83. All right, now let's see if we could come up with a shortcut here to find the amount at the end without finding the interest and adding it back. So each time we have been finding 1.5% of the total that I have and then adding it back. Well, a shorter way might be, instead of taking that extra step to add it back, to find 101.5%. So the 100% would be keeping what I already have, and then we're going to add that back. So let's see if our shortcut would work here. If I start with $5,000 and multiply this by 1.015. So the 1 is the 100% that I keep, that 5,000, and then this 0.015 is the interest that I'm earning. And do you see how that took us from here to here? I just multiplied by 1.015. So again, to get from here to here without that extra step of adding it back, I can multiply by 1.015. So I'm going to take that result and multiply by 1.015, and it just saves me a step. And then take that, multiply it by 1.015, and then multiply this by 1.015. Alright, and then multiply this by 1.015. And then lastly, one more time, 1.015. Alright, so here our shortcut then is going to be to multiply by 1.015, which just saves us that step of adding things back to what we already had. Alright, so we had 5,386.42. And then we ended up with 5,467.22. Alright, and then we see here, again, as we suspected after the first year, when I'm paid once a year, I end up with this much. Twice a year, I end up earning, about a little less than $4 more. So I hope you have some concept of the more often I'm paid, the more money I will accrue, because that money starts earning me interest immediately. Alright, so now when we move to the quarterly case, I want to see if we can generalize what we did here in red to kind of save us some time. Okay, so we took the 1, right, which is the 100%, the principal, what I already have that I keep, point, and then we take our interest rate and we're going to multiply it by that 5,000. 1, 2, 3, 4, 5, 6 times. Now why 6 times? Because I was paid twice a year for 3 years. Okay, so another way that we might write this is I start with $5,000 and I'm going to multiply this by 1.015 6 times. Well, our shortcut for that is to raise this to the power 6. Now let's see if that shortcut gets us to the same result. 5,000 times 1.015 to the power 6. and it does. Much, much, much quicker. So let's see if we could do the same thing for our quarterly case. All right, so I am again going to start with $5,000 times 1 point. Now, here I have 3%, right? But I'm going to be paid 4 times a year. So I'm not going to get the 3% all 4 times. I need a fourth of 3%. So I'm going to take my 3% and I'm going to divide it by 4. Okay, now this is scientific notation, which would be 0.0075. Okay, now how many times am I going to get paid? If I get paid 4 times a year for 3 years, would that be 12? So we're going to get 12 up here. Now where in the world did that 12 come from? Well, quarterly, 4 times a year for 3 years. Alright, let's see if this little shortcut here is hopefully going to be much, much quicker than what we were just doing. $5,000 times 1.0075, so I get 0.75% 4 times a year, raised to the 12th. Alright, so then we end up with $5,469.03. Alright, so if we wanted to go monthly then, alright, so I have my 3% for the year, but I'm going to divide that by 12 because I'm paid 12 times a year. We get 0.0025, so a quarter of a percent. So again, I'm going to start with 5,000. 1 point, because that's what I'm going to keep. Now I'm going to get a quarter of a percent every month. So a quarter of a percent times 12 months would give us the 3% annually. Now let's see how many times we get paid. We get paid 12 times a year for 3 years. I think that would be 36 times we're getting paid here. And where in the world did this 36 come from? That was 12 times a year, monthly, for 3 years. Alright, here. So we have 5,000 times 1.0025 raised to the 36 times I'm getting paid here. Alright, so we get $5,470.26. Alright, so hopefully we can see that the more times we're paid, I earn a little bit more money here. Alright, now let's come back to that first slide. We want to generalize what we just did here. Okay, so the amount that we end with, we're going to call that A. So this is what we have at the end. Okay, the T is how many years. Okay, P is the principal. This is what we start with. R is our interest rate, and this should be as a decimal for this formula. You might see other versions that take it as take the percent and divide it by 100, but we're going to go ahead and change that to a decimal. And then N is the number of times we are paid each year. So N, for example, If it was quarterly, I'm paid 4 times. All right, so what did we do? We started with that $5,000 P, right? And we multiplied it by 1 point something. So how did we come up with that? Well, it was always 1, right? Because we're going to keep what we already have in the bank, that 100%, plus. Now, if we look over here at that decimal portion, how did we come up with this 0.015? Or how did we come up with here this 0.0075 or 0.0025? Well, what we did was we took the interest rate as a decimal, because this is what we're going to get for the whole year, but we divided that by how many times each year we were paid. Okay, so in the semi-annually version, we took our 3% and divided by 2 because we got 1.5% halfway through the year and 1.5% at the end. Okay, then we raised this to some power. Well, where did that power come from? That's how many times we got paid. So we got paid n times for t years. So let's look back here. In this case, we got paid 6 times, right? Twice a year for 3 years. 2 times 3. In this case, we got paid 12 times. 4 times a year for 3 years. Or 12 times a year for 3 years for a total of 36 for the monthly. Alright, so hopefully you can see this generalized version here, where that comes from. Now, it is very important that you put parentheses here and that you put parentheses around your exponent. Otherwise, when you type it into the calculator, it's only going to raise that to the n and then multiply it by t. Okay, so this is our discrete case. Now, the continuous case is not as obvious. So I'm going to give you this formula. We still have a at the end. We still start with p. Now, if I am paid every single time I earn a bit, we have this e here, which is not a variable. E here is that special number that we saw earlier. If I, which is about 2.718, I believe. So if I go second natural log e to the first is 2.78281828, and it goes on and on. You can think of this as similar to pi. This is an irrational, very special number. All right, and then we're going to take that and raise it to the RT. Okay, and again, make sure you have parentheses around your exponent when you type this in. And you might want to make a note, this is a special number, which is about 2.718. Okay, but we will use the unrounded version that's built into our calculator. Alright, so let's go back here. If we are paid continuously, every time I earn a penny, it is immediately deposited into my account and starts earning me more interest. We would have 5,000, which is our principal, times E, that special number, to the power. Now, what was my interest rate? 3% times 3 years. All right, let's see if we can find what that would be. 5,000 times E. Do you see it's in yellow above natural log? So I'm going to hit Shift, natural log. Now I need to put parentheses around that exponent. 0.3% interest times 3 years. And we get $5,470.87. All right. So hopefully this has helped us understand that the more often we are paid, the more money we earn, and hopefully by going through this the long way, this discrete formula here makes a little more sense to you. All right, so let's work through a couple examples. In this first example here, you invest $8,000 at 2.5% interest compounded quarterly, and we want to know how much you would have in 5 years. All right, the first thing that is important to me is this word quarterly here. Okay, so this tells me I'm going to use my discrete formula, right? So that A equals P times 1 plus R over N all to the NT. All right, and it also tells me what N is. If I'm paid quarterly, N is 4. All right, so let's see if we can go back, reread this, and pick out what these other variables are. So you invest $8,000. So this is what we start with. This is our principal P. All right, that interest rate is 2.5%. So when we change that to a decimal, we get 0.025. We want to know how much we would have. How much would you have? All right, so this is saying I am looking for A. This is what we're trying to find, right? How much we would have at the end, and our T is 5. We can now plug this into our formula. So A is what we're looking for. P is $8,000. 1 plus my interest rate is 2.5% as a decimal. We're going to divide that by 4 because it's quarterly, and then we're going to get paid how many times? 4 times 5, or 20 times. Okay, just make sure that we have parentheses here and here when we type this into our calculator. $8,000 times, in parentheses, 1 plus 2.5% as a decimal divided by 4, close the parentheses, raise that to our exponent, open the parentheses, 4 times 5. Alright, so we get $9,061.66. Alright, not too bad there. Alright, next you invest $7,500 at 3.25% compounded continuously. We want to know how much we would have in 7 years. Alright, so this word right here, continuously, lets us know we're going to use that other version of our formula. Okay, so our initial investment, P, is $7,500. Our interest rate here as a decimal is 0.0325. There is no N here, right? Because there is no fixed term when I'm paid. However, T is 7 years. So A is what we're looking for, right? How much would you have? A is what we're trying to find. So we're going to start with that $7,500. Multiply that by E, this special number, raised to the power 0.0325 times, how many years are we going here? 7. Alright, so we have $7,500 times, to get our E, see it's in yellow above natural log, we have to hit shift natural log, open the parentheses for our exponent, 0.0325 times 7. Alright, so we end up with $9,415.93. Again, not too bad. We're just picking the right formula and plugging those in. Next, we want to know how much would you need to invest now in a single lump sum deposit. Alright, so this is how much would you need to invest now. We are looking for this value here, P. So that we would have 3%, or at 3%, so R is 0.03, compounded monthly. Alright, if this is monthly, we know we're using our formula here for discretely compounded interest. And more importantly, monthly, we know that N is 12. Okay, to have $6,000, so this is not what we're putting down, this is what we want to end with. This is A, after 12 years. Alright, so let's see if we can plug in here what we know. A is going to be $6,000. R is 0.03. N is 12. And T is also 12. Okay, so we end up with 6,000 equals P times 1 plus 0.03 over 12 to the 12 times 12. Alright, now we're going to have to do a bit of algebra to solve for P. Now, all of this stuff, do you see there's no variable there? All of that is just a number. So let's figure out what that number might be. So I'm going to have 1 plus 0.03 divided by 12 raised to the power, in parentheses, 12 times 12. Alright, so that number is 1.433. Alright, now, if we want to solve for P, we would divide both sides by that number, 1.433. Now, just to make sure I don't have any rounding error, I am going to use my answer command. So I'm going to take $6,000 divided by, well, I want to divide it by this result here before I rounded it. So I'm going to hit shift and the negative sign for my previous answer to get that I need to put down $4,187.94. Alright, so I would have to put down today $4,187.94 such that I would have $6,000 at the end of 12 years. All right, how much would you need to invest now? So this is another problem where I am looking for P, the principal, so that I would have at an interest rate of, if I change this to a decimal, 0.0425. If I'm compounded continuously, all right, so I'm going to use this. A equals PE to the RT. Such that I would have $4,500. This is A, what I would have at the end after 7 years. Alright, so A, what I end up with is 4,500. P is what we're looking for, that's our variable. E is 2.718 about, but we're just going to use that button in our calculator. We know the interest rate here is 0.0425, and lastly we're investing for 7 years. So let's see if we can plug all that into our formula. Alright, now we need to make sure we have parentheses around that exponent, but again, just like in the last time, all of this is just some constant, some number. So to figure out what that number is, I'm going to hit Shift Natural Log, open the parentheses for my exponent, 0.0425 times 7. Alright, so this is about 1.346. Okay, and then to solve this, we would then divide both sides by 1.346. But so I don't have any rounding error, I'm going to use that answer command that we just used. So I'm going to take my $4,500 and divide it by second answer, the unrounded constant here, and we get that we would have to invest $3,342.03. All right. Next, we want to know how long. All right, so now this is something new. We haven't seen one like this. How long? I am looking for T here. Would it take an investment to double? All right, now this is something new also. I don't tell you what we start with. I just tell you that when we're done, we want twice as much. At 4% interest compounded continuously. Alright, so I know that R is 4%. And we are looking for T. Now, I do not tell you what A and P are. So let's see what we know here. Let's say I start with this. A equals P E to the 0.04 T. Now, here's the tough part. Let's say I started with $1. If I start with $1, and it doubles, I end up with $2. All Alright, so I end up with the equation 2 equals e to the 0.04 t. Alright, well, let's say I start with $100. So if I started with $100, I would end up with 200 e to the 0.04 t. Now, if I was solving this for t, the first thing I need to do is divide both sides by 100. And I am left with, the hundreds cancel out, 200 divided by 100, I am left with 2 equals e to the 0.04 t. So do you see I end up with the same equation whether I started with $1 or I started with $100? So let's say I start with P here, some principal amount that I don't know. Well, if it doubles, instead of A, I'm going to end with 2 times P, e to the RT. Okay, so this might be a little abstract. We don't know what this P is, but you see I have a P on both sides of my equation. So if I divide both sides by P, these P's are going to cancel, and again we end up with 2 equals e to the 0.04 t. So no matter what we start with, if it doubles, I end up with this same equation. Now, we need to solve this equation for t. So we've got 2 strategies here. If you remember the properties of logs, to solve this equation, the opposite of this e would be a natural log. So I could take the natural log of both sides. Okay. Our second strategy, which we'll do next, would be to use the technology to solve this, where we either use our graph menu and find the intersection, or we use the solver. Alright, so let's say I take the natural log of both sides here. Natural log of this equation, 2 equals e to the 0.04 t. Okay, these are inverse operations, so this piece, those are going to cancel, and I'm left with the natural log of 2 equals 0.04 t. Alright, then I divide both sides by 0.04, and I get the result here, natural log of 2 divided by 0.04. So we get 17.329 years. Alright, so no matter what I started with, if my interest rate is 4% compounded continuously, it's going to take me 17.329 years to double. Alright, so let's see if we could arrive at that same result using the technology. Alright, so again, if I want to solve this equation here, I'm going to put the left hand side in y1, which is just 2, the right hand side in y2, e to the 0.04. Now instead of t, I'm going to use the variable x theta t button here. Now we need to pick a window here. So if we're thinking about an investment doubling, that's definitely going to be positive. All right, so let's go start maybe 0 to 50 years. If we don't see our result in this window, we might have to try again. So I'm going to draw this, do a shift zoom auto. Alright, so this is my 2, the blue line. The red line is my e to the 0.04 t, and we want to know when those are the same where they intersect. shift graph solve intersection. And we get the same result, 17.329. All right, last one here. We're looking for a doubling time, so we want how long. I'm searching for t. Would it take an investment to double? Okay, so if we start with p, we end with 2p. If my interest rate is 0.0375, but if we're compounded quarterly, we're going to use our discrete formula where n is 4. Alright, so I want to know, I'm going to end with 2p when I start with p times 1 plus my interest rate is 0.0375. I'm paid quarterly, so this is going to be 4. Raised to the power 4t, which is what I'm looking for. Okay, and as we saw before, I have a p on both sides, so these p's are going to end up canceling. So the equation I'm attempting to solve is 2 equals 1 plus 0.0375 over 4 to the 4t. Okay, now this piece inside the parentheses here, this base is just a number. Okay, so we can take the natural log of both sides so that we can then bring down our exponent. So let's first, just to simplify things, figure out what that number might be. If I take 1 plus 0.0375 divided by 4, we get 0.009375. All right, now we're going to use our property of logs. If I take the natural log of both sides, well, this allows me to take my exponent down here and bring it down as a constant multiplier. So we have now the natural log of 2 equals 4t times the natural log of 1.009375. Okay, now we're getting closer. To solve this, I want to divide both sides. Well, I want to keep t, right? So I want to get rid of the 4 and the natural log of 1.009375. All right. So now, if I take the natural log of 2 and divide it by, in parentheses, 4 times the natural log of 1.009375, we get 18.57 years. Now there's just one problem here. If you remember, we're only paid quarterly, so I would be paid at year 18. I wouldn't be there yet. 18 and a quarter, 18.25. Wouldn't quite be there yet. 18 and a half, 18.5. I'm not quite there, but you see I'm not going to get paid at 18.57. I'm not going to get paid again until the next quarter. So it would end up, even though theoretically I would earn that money at 18.75, the bank's not going to pay me until my next pay period, which is 18.75 years. Okay, now if all of this algebra that we did here is hurting your brain, we can enter this into the calculator at this step right here and find the intersection. So let's see if we can do that. I'm going to go to my graph menu. In y1, I'll put the left hand side 2. In y2, I'm going to enter my equation. But just make sure that you have parentheses around that exponent. Alright, I think my window is still 0 to 50 years as it was before. I do a zoom auto, but I can already pretty much see what's going on here. And to find the point at which these are equal is where they intersect. And we again get 18.57, but realizing that I'm paid discretely, I'm going to have to wait until that next pay period, which would be 18.75.